Something happened today that should make everyone stop and pay attention, because this is not a theory, not a simulation, and not a distant possibility. It is a measured event recorded by multiple observatories across the planet, and it began quietly, so quietly that most of the world hasn't noticed yet. February 26, 2026. 4 hours before this message is being recorded, a single data point appeared on a screen at the Apache Point Observatory in New Mexico. At first glance, it looked ordinary. Another laser returned from the moon, another routine measurement in a process scientists have repeated thousands of times. But within minutes, that calm routine collapsed. The signal came back too early. Not slightly early. Not within the margin of error. It came back impossibly early. For more than half a century, scientists have tracked the moon's orbit using laser ranging. Astronauts left mirror arrays on the lunar surface during the Apollo missions, and ever since, observatories have fired laser pulses at those mirrors to measure the exact Earth-Moon distance. The precision is staggering. We don't estimate the moon's position, we know it down to millimeters. We know how it drifts. We know how it breathes as it slowly spirals away from Earth year after year. This system is so reliable that it's considered boring, predictable, finished science. Until this morning, at exactly 9:14 UTC, the return pulse from the moon arrived faster than physics allows. The initial assumption was simple and comforting. Atmospheric distortion, timing drift, maybe a software hiccup. The team recalibrated and fired again. The signal returned even faster. They fired again. Same result. Within minutes, alerts were sent out. Independent observatories were asked to verify the measurement. France confirmed it. Italy confirmed it. Different equipment, different teams, identical data. The moon was closer than it should be. Not by millimeters, not by centimeters, by miles. In the last 18 hours, the moon has moved approximately 14 miles closer to Earth. That number is not dramatic language. It is a measured displacement of 22.5 kilometers. To understand why this is alarming, you have to understand what it takes to move an object like the moon. This is a body with a mass of 73 quintillion tons, locked in a stable orbit for 4.5 billion years. You don't nudge something like that accidentally. You don't move it without injecting an almost unimaginable amount of energy into the system. This was not a glitch, not a faulty sensor, because while astronomers were still rechecking equations, Earth itself began to respond. Tidal gauges started reporting anomalies. Water levels in the North Atlantic rose several inches above predicted highs. In the Bay of Fundy, currents accelerated beyond what existing models allow. These are not long-term effects. They happened immediately. The oceans reacted because gravity changed. At the center of this event is an object known as 3I, Atlas. Until recently, it was dismissed as another interstellar wanderer, a dark comet or rogue body passing quietly through our solar system. Yesterday, scientists believed it would come and go without consequence. Today, that assumption is gone. The data shows that 3I, Atlas didn't simply pass by. It interacted, and not weakly. The most unsettling question facing astrophysicists right now isn't how this happened, it's what happens next. If something pulled the moon 14 miles closer today, what prevents it from pulling it further tomorrow? To grasp the scale of this threat, you need to understand just how stable the moon's orbit normally is. Over decades, its distance from Earth is known to within 3 centimeters. Laser pulses bounce off lunar mirrors, return times are measured, and the calculations line up perfectly. It is routine science. Except on February 24, 2026, when routine broke. At 6 UTC, Apache Point fired a standard pulse at the Apollo 15 reflector. The return arrived 75 microseconds early. At first, it didn't raise alarms. By 8:30 UTC, the deviation had grown. The moon was physically closer than it had been just hours before. This wasn't a wobble, this wasn't noise, it was a trajectory change. And that realization marked the moment when scientists understood that something massive, unseen, and deeply abnormal had entered the Earth-Moon system. And this was only the beginning. To understand why this shift sent shockwaves through the scientific community, you need context. The moon naturally drifts away from Earth at about 1.5 inches per year. That slow retreat is caused by tidal friction and has been measured consistently for decades. It is one of the most stable, predictable processes in orbital mechanics. But within a single morning, that drift didn't just stop, it reversed. And it didn't reverse gently. It accelerated by a factor of millions. NASA's Lunar Reconnaissance Orbiter, currently circling the moon, provided the next piece of confirmation. Its telemetry showed something that should never happen. The spacecraft's orbit became unstable. Its altitude dropped by nearly 400 meters, not because the orbiter malfunctioned, but because the moon itself was moving. Its gravity well shifted as the entire lunar body was dragged closer to Earth. This wasn't speculation anymore. 3 independent systems had now confirmed the same impossible event. The moon had lurched inward by 14 miles. The verification came from 3 continents: Apache Point Observatory in New Mexico, Côte d'Azur Observatory in France, the Matera Laser Ranging Observatory in Italy. Different lasers, different clocks, different atmospheres, same result. The moon had been pulled off its predicted path. That alone would be historic, but the real question was what could possibly cause it. The answer points directly to 3I Atlas. Discovered in late 2025, it was initially cataloged as a rogue comet entering the inner solar system from interstellar space. At first, nothing about it seemed extraordinary. But as it approached, scientists noticed something odd. It didn't behave like a comet. There was no outgassing, no visible tail, no brightening as it crossed the frost line. It stayed dark, compact, and strangely heavy. Then, on February 24th, as 3I Atlas passed within 0.8 astronomical units of Earth, it did something that should not happen under normal physics. It slowed down. Objects falling through gravitational fields accelerate. They don't decelerate unless acted upon by another force. But at precisely the moment 3I Atlas lost velocity, the moon was pulled inward. The timing wasn't approximate. It was exact. 9:14 UTC. This correlation is impossible to ignore. Orbital analysis shows that the gravitational influence required to move the moon by 14 miles demands a mass far greater than anything a comet-sized object should possess. The numbers force a disturbing conclusion. Whatever 3I Atlas is, its mass does not match its size. NASA's Deep Space Network then added another layer to the mystery. While tracking the object, scientists detected a gravitational lensing effect. Light from background stars bent as it passed near 3I Atlas. This phenomenon is normally observed around massive galaxies or black holes, not small objects drifting through the solar system. The degree of lensing suggested a mass equivalent to roughly 40% of the moon, compressed into an object less than 50 kilometers wide. That level of density borders on the absurd. It rules out rock, ice, metal, or any known planetary material. It points instead towards something exotic, something ancient, possibly a fragment of a neutron star, or something even stranger. One theory rising rapidly among astrophysicists is that 3I Atlas contains a primordial black hole, an object formed in the first moments after the Big Bang, wrapped in a shell of normal matter that disguises its true nature. If that sounds extreme, Consider the alternatives. Even a solid iron object would need to be the size of Mars to exert this kind of gravitational pull, but telescopes show nothing that large. The paradox is unavoidable. A small object is behaving like a planetary mass. As if that weren't enough, the moon itself began to respond in ways no one expected. Seismometers placed on the lunar surface during the Artemis 3 mission started recording intense activity. These weren't the gentle thermal quakes seen during the Apollo era. These were sharp, violent events registering magnitudes as high as 5.8. The moon wasn't just moving, it was straining. At the same time, Earth's oceans reacted instantly. In the Bay of Bengal, water levels rose 12 centimeters above prediction. In the North Sea, 9 centimeters. These are not long-term climate effects. They are direct gravitational responses. Physics is clear. Tidal force increases dramatically as distance decreases. Even a small change in lunar distance produces an outsized effect on Earth's oceans. And the most unsettling detail of all is this. 3I, Atlas hasn't left. Its trajectory shows that it lost energy during this interaction. That means it wasn't just passing through. It may now be bound to our solar system, which means this was not a one-time event, and the next pass may be far worse. What makes this situation especially disturbing is how controlled the event appears to have been. The moon wasn't yanked violently or chaotically. The data shows a smooth, deliberate reduction in its orbital velocity, almost as if something carefully reached out, grabbed it, and pulled. That kind of precision is not how natural gravitational encounters behave. Random flybys create noise, spikes, irregular curves. This looked more like a capture maneuver. Classical gravity, as described by Newton, is straightforward. Mass attracts mass. Bigger objects pull harder. A passing comet, no matter how fast or oddly shaped, should have an almost negligible effect on the Earth-Moon system. It's like a grain of sand drifting past a freight train. It doesn't slow the train. It doesn't change its path. Yet 3I, Atlas didn't just perturb the system. It altered it. To pull the moon 14 miles closer to Earth in less than a day requires an almost incomprehensible amount of force. We're talking about a gravitational influence equivalent to billions of Saturn V rockets firing simultaneously in perfect alignment. No comet, no asteroid, no conventional object can produce that. Even if 3I Atlas were made entirely of iron, it would still fall short by orders of magnitude. The paradox deepened when data from the European Space Agency's Gaia spacecraft was analyzed. Gaia tracks the positions of over 1 billion stars with extreme precision. As 3I, Atlas passed through its field of view, something strange appeared in the data. Background starlight bent slightly, subtly warping as it passed near the object. This bending, known as gravitational lensing, is usually associated with massive galaxies or black holes. Seeing it caused by something inside our own solar system was unprecedented. This lensing wasn't strong enough to indicate a stellar mass black hole, but it was far too strong for a comet. The distortion pattern suggested a compact, ultra-dense core surrounded by a relatively thin shell of ordinary matter. In other words, something heavy, wearing a light disguise. That's why the theory of a primordial black hole has moved from fringe speculation to serious discussion. Primordial black holes are hypothetical objects formed in the first fraction of a second after the Big Bang. Unlike the black holes created by collapsing stars, these can be small, even microscopic, while still carrying immense mass. Some models predict they could roam the galaxy, invisible unless they pass close enough to disturb something massive, like, for example, a moon. If 3I, Atlas contains such an object, it would explain nearly everything. The extreme density, the gravitational lensing, the lack of outgassing, the the ability to steal orbital energy from the moon. It would also explain why the interaction happened in steps rather than as a continuous pull. The Lunar Reconnaissance Orbiter's data shows that the moon's inward motion occurred in 3 distinct jolts. The first at 9:14 UTC, moving at roughly 4 miles. The second at 12:30 UTC, adding another 6 miles. The third at 15:45 UTC, completing the 14-mile shift. Between these events, the motion paused. Gravity doesn't normally work like that. It doesn't stutter. Unless the source itself is rotating, a rapidly spinning ultra-dense object can drag spacetime around with it. This effect, known as frame dragging, has been measured around Earth using specialized satellites, but the effect is tiny. Millimeters over years. What we're seeing here is frame dragging on a lunar scale, happening over hours. That implies a rotation rate approaching relativistic limits. In simple terms, space itself may be twisting around 3I Atlas, and the moon briefly got caught in that twist. Each time the orientation lined up just right, another jolt of gravitational energy transferred. That would explain the step motion, the pauses, and the precise timing. And here's a consequence almost no one outside the scientific community is talking about yet. By pulling the moon inward, 3I, Atlas lost energy. That means it slowed down. Objects that lose enough energy don't escape. They stay. Orbital models now show that 3I, Atlas, is no longer on a hyperbolic exit path. It has entered an elliptical orbit around the Sunday. It's coming back. In approximately 45 days, it will swing through the inner solar system again, and if it pulled the moon 14 miles closer on this pass, there is no guarantee the next interaction will be weaker. In fact, orbital mechanics suggest it could be stronger. The moon is still ringing from the stress of the first encounter, and that stress didn't just move the moon. It changed Earth itself. As the moon shifted inward, the balance of the entire Earth-Moon system changed in subtle but measurable ways. The barycenter, the point around which both Earth and the Moon orbit, moved by roughly 8 meters. That number sounds insignificant until you understand what it affects. An 8-meter shift is enough to slightly alter Earth's rotation. It can change the length of the day by microseconds. It can disturb satellite orbits. It can amplify existing instabilities in Earth's axial wobble, and that wobble is already responding. NASA's Goddard Space Flight Center reported an unexpected anomaly in the Chandler wobble, the slow, natural drift of Earth's rotation axis. The wobble intensified beyond predictive models. This isn't a long-term climate issue. This is a real-time mechanical response to a sudden redistribution of gravitational forces. GPS satellites are already applying micro-corrections. Navigation systems are compensating. The planet is adjusting. But while attention was focused on Earth's oceans and orbital math, something far more alarming was unfolding on the moon itself. On February 24th at 14:15 UTC, seismometers deployed during the Artemis 3 mission detected a signal that lunar scientists were not prepared to see. Traditional moonquakes are deep, slow, and gentle. They originate hundreds of kilometers below the surface and can last for hours as vibrations echo through dry rock. This was different. This was sharp, violent, and shallow. The signal lasted exactly 11 minutes. Its epicenter was traced to Mare Serenitatis, one of the moon's largest mass concentrations, known as a mascon. Mascons are dense regions of crust that already distort local gravity. They are geological weak points under stress. And the data showed that this stress finally exceeded the moon's tolerance. 2 hours later, the Lunar Reconnaissance Orbiter passed over the region and captured images that confirmed the worst fears. A fracture had opened across the basin floor. a fissure nearly 4 kilometers long, cutting through terrain that had been stable for billions of years. The moon's surface hadn't just shaken, it had split. This alone would be historic. But what came out of that crack changed the situation entirely. Spectral analysis of the venting material revealed high concentrations of radon-222. Radon is a radioactive gas produced by the decay of uranium deep within planetary bodies. On the moon, it usually seeps out slowly over geological timescales. Detecting it in large quantities means the fracture reaches deep into the lunar mantle. The moon wasn't just cracked, it was opened. The implication is unavoidable. The gravitational stress from 3I Atlas didn't merely tug on the moon's orbit, it compressed and stretched the moon internally, generating frictional heat. This is the same mechanism that makes Jupiter's moon Io the most volcanic object in the solar system. Constant squeezing turns orbital energy into heat. If this process continues, the moon could become geologically active again. Think about that. A world long considered dead may be waking up. If internal melting begins, magma could rise. Volcanic vents could reopen. The moon we see in the sky could change its appearance within a human lifetime. This isn't speculation. This is a known physical process observed elsewhere in the solar system. And the effects wouldn't stop at the moon. As the moon's internal mass distribution changes, its orbit becomes less stable. That instability feeds directly into Earth's tides. The modest surges we're seeing now, 4 inches in New York, 9 centimeters in the North Sea, are early signals. If the moon enters a sustained heating cycle, tidal behavior on Earth could become erratic. King tides could occur monthly. Coastal flooding would no longer follow predictable lunar calendars. But there's one more detail that elevates this from a natural disaster scenario to something far more unsettling. The fracture in Mare Serenitatis isn't just venting gas, it's emitting a signal. Deep space monitoring stations picked it up at 16 UTC, not random noise, not chaotic vibrations. A low-frequency pulse repeating every 11 minutes and 23 seconds. Perfectly regular. Geological processes don't keep time. They don't produce clean, periodic signals. This does. Which raises a question no one is comfortable answering yet. Is the moon simply resonating under extreme gravitational stress, or is it being driven into resonance by 3I Atlas itself? Because if the Earth-Moon system enters a gravitational resonance with that object when it returns in 45 days, the 14-mile shift we just witnessed will look trivial. Resonance amplifies motion. It destroys structures. It reshapes systems. And the clock, right now, is running. To understand why that rhythmic signal is causing such alarm, you need to understand what resonance really means in physics. Resonance isn't force, it's amplification. A small, repeated input applied at the right frequency can produce massive effects. That's how a singer can shatter a glass without touching it. That's how bridges collapse under steady footsteps. And that's why engineers fear resonance more than raw power. The pulse coming from the lunar fracture is repeating every 11 minutes and 23 seconds. That interval is not random. When scientists overlaid the timing with the predicted gravitational influence cycles of 3I Atlas, the match was unsettlingly close. The moon appears to be responding directly to the passing object's gravitational field, vibrating at a frequency that allows energy to build instead of dissipate. In simple terms, the moon may be ringing like a bell, and each pass of 3I Atlas is striking it again before the vibration can fade. If this is purely geological, the result would still be catastrophic. Continued resonance would mean increasing internal heat, widening fractures, and renewed volcanic activity. Lava flows on the moon are not science fiction. We know how tidal heating works. We've watched it reshape entire worlds. Io, Europa, and Enceladus are proof. A geologically active moon would permanently alter Earth's night sky and destabilize our tides for generations. But there is a more dangerous possibility. The frequency detected is not just compatible with lunar resonance, it also travels efficiently through rock, water, and planetary crust. That means the vibration doesn't stop at the moon, it propagates. Subtle signals of that propagation are already being detected on Earth. Sensitive instruments have picked up faint correlated oscillations in deep ocean pressure sensors and borehole seismometers, not earthquakes, not storms, something quieter, something rhythmic. If the Earth-Moon system locks into a shared resonance state, the consequences scale rapidly. A 14-mile orbital shift could become 40 or 100, and tides would no longer rise by inches, they would rise by tens of feet. Coastal geography would change in a single lunar cycle, ports would flood permanently, estuaries would collapse, salt water would surge inland, contaminating freshwater systems. Entire cities, New York, Tokyo, London, Shanghai, would face conditions no infrastructure was built to survive. And none of this requires impact, no collision, no explosion, just gravity, applied with precision. The timing makes this even more unsettling. Orbital projections show that 3I Atlas will return to its closest point in approximately 45 days. During that window, its trajectory aligns almost perfectly with the plane of the moon's orbit. That alignment maximizes tidal coupling. It is the worst possible geometry. Meanwhile, the object itself is behaving in ways that suggest it is not a passive mass. Its trajectory adjustments are too smooth, its energy loss too controlled, its gravitational effects too localized. If it were merely a fragment of exotic matter, we would expect chaos. Instead, we see structure. And that brings us to the question scientists are avoiding in public briefings. Is 3I Atlas simply an ancient relic drifting through space, or is it an active system? The distinction matters. A dead object obeys physics blindly. An active one can adapt. It can interact. It can respond. The step nature of the moon's movement, the timing of the pulses, and the precise energy transfer all point toward regulation rather than randomness. No one is claiming intent yet, but the data is forcing a reconsideration of assumptions that have held for centuries. Right now, Apache Point Observatory is firing laser pulses at the moon every second. The distance is being updated in real time. The margin of error is less than the width of a human fingernail, and the moon is still closer than it was yesterday. 3I Atlas is currently about 0.9 astronomical units away, completing the far end of its loop. Its velocity profile confirms it is bound. It will not escape. It will return. The instruments are watching. The seismometers are listening. The oceans are rising. And what happens next depends on one thing we still don't understand, whether the signal from the moon is a symptom or a response. If the signal is a response, then it means the moon is not just reacting to stress, but synchronizing with it. That distinction changes everything. A symptom fades when the cause weakens. A response strengthens as the interaction continues. And all current measurements suggest the latter is happening. The amplitude of the lunar pulse has increased by nearly 6% over the past 72 hours. That growth is small, but it is steady, and in resonance systems, steady growth is the most dangerous pattern of all. Earth's monitoring networks are now operating in full coordination. Tidal gauges, laser ranging stations, satellite altimetry, and seismic arrays are feeding into shared models around the clock. What these models show is deeply unsettling. If the resonance continues at its current rate, the moon's orbital eccentricity will increase measurably within weeks. That would introduce uneven tidal forces, meaning the oceans would no longer rise and fall symmetrically. Some coastlines would experience extreme surges, while others see abrupt retreats. The ocean would stop behaving like a predictable system. That instability feeds back into Earth itself. Uneven tidal loading alters stress on tectonic plates. Fault lines that were once stable could become primed, not triggered by earthquakes from below, but pulled from above. This is a mechanism we know exists, but have never seen activated at scale. Even a small increase in seismic probability spread across the planet represents a global risk. At the same time, the moon's changing gravity would affect satellites, space stations, and deep space missions. Orbits that were calculated years in advance would drift. Corrections would consume fuel. Some assets would become unrecoverable. Space, which we treat as stable and empty, would become a dynamic environment again.